Our homework questions for last night were page 486, 1 to 2, and 5 to 10. We got a request to go over number 5, number 7, and number 10. So we'll take a look at number 5 first. Give 2 examples other than those in the text of possible collinear collisions. By the way, what's that term mean, collinear collision? You haven't heard that term, have you? Well, up until the time you did these questions, it's the only kind of collision you did. A collinear collision is a collision that's in one dimension. So north-south or east-west or some kind of combination, but all along the same axis. Okay, so it's the collisions that we did up until with about 5 minutes left in class yesterday. 2 examples of collinear collisions between 2 identical masses. Include a sketch of each situation showing the velocity of each object immediately before and immediately after the collision. Maybe with this question, it's just a matter of kind of what the heck do they mean exactly by it. So we're talking about a collisions in one dimension. So we'll say object number 1 and object number 2, both moving along the same axis. So maybe they're moving towards each other like this. Okay, they collide with each other, and then they're going to bounce off. Well, if they collide with each other at the same speed like they have right here, right? This speed is the same as this speed, then they're going to bounce off of each other such that they're going this way and this way with the same speed. If they have the same mass and they have the same speed in opposite directions, then they're going to bounce off of each other like that. Matt, does that make sense? Yeah. Okay, so let's take a look at another situation now, because we're looking for 2 examples here. We're talking about, I think it says identical masses, yeah. So we're talking about object number 1 and object number 2 still having the same mass, but now maybe a different velocity. Object number 1 is moving towards object number 2 like this. Object number 2 is moving towards object number 1 like this. What's going to happen? What's going to happen to these? Well, depending upon what those velocities are, it's entirely possible that object number 2 ends up going back afterwards like this, and object number 1 continues to move forward like this. Does that make sense? Now, we could calculate some numbers there to determine all of these different possibilities, but there's 2 possibilities for it. Did anybody have a different possibility that they wanted to check? Yeah? Okay, good one, yeah. So we've got object number 1 moving towards object number 2 that is at rest, that's stationary. Okay, if they're equal masses, they're going to bounce off of each other. What's going to happen is object number 2 will end up moving this way, probably with a velocity that's a little bit less there. And object number 1 will likely continue moving that way as well, but with a smaller speed. Greg, is that more or less what you had? Good. You get the idea there?
Yeah.
Okay. Okay, fair enough. Yeah, fair enough. I should have mentioned that term to you before. But as a general rule of thumb, guys, understand this. If I haven't given you a term, or if I haven't given, this happens sometimes as we go through the year on quizzes. We get 4 possible answers, right? A, B, C, D, and you look at D and it's like, oh, I've never heard of that term. Well, I don't know what that means. It's not the answer. Okay, so basically I'm telling you, if I haven't taught it to you, it doesn't really matter what it is at this point. So the term collinear, well, that's an important word. They're telling you it's a one-dimensional collision, but at that point when you're doing this question, it's the only kind of collision you've done, right? So you got to say, okay, I haven't learned that word. So what kind of collision do I know about? Well, there's only one kind of collision that I know about, okay? Now, I should have said that to you still, but now you know if something like that happens down the road, you know how to deal with it, right? All right, what's our next question, number 7? It says a liftoff, a space shuttle has a mass of 2.04 times 10 to the 6 kilograms. The rocket engine expels 3,700 kilograms of exhaust gas during the first second of liftoff. Now, gas is cheap compared to what it has been in the past. It's under 80 cents. I was in Edmonton on the weekend. I paid 57 cents a liter. I haven't paid 57 cents a liter since 1995. But this space shuttle is using 3,700 kilograms in the first second. I don't care how cheap fuel is, this is still expensive. Okay, 3,700 kilograms in the first second. This is giving the rocket a velocity of only 5.7 meters per second upwards. What is the velocity of the exhaust gas leaving the rocket engines? They're telling me to ignore the change in mass due to the fuel being consumed. In other words, As the space shuttle burns fuel, the space shuttle actually gets a little bit lighter. They're telling me to ignore that. Why? Well, because even though in the first second it gets 3,700 kilograms lighter, it doesn't really matter, right? The space shuttle is so heavy, the fact that it's 3,700 kilograms lighter is like the equivalent of you driving in your car throwing a quarter out the window, right? You're a little bit lighter as a result of throwing that quarter out the window. Does it really matter in the grand scheme of things? No. Okay, so the exhaust gas coming out the space shuttle is effectively the quarter coming out your windshield. All right. So what is this? It's an explosion, right? We've got this space shuttle that has this fuel in it, and then this exhaust gas goes at the back, goes one way, the space shuttle goes the other way. Which one do you think is going to be going faster, the exhaust gas or the shuttle? What's your prediction there? Exhaust gas going faster, shuttle going faster? Why? Why would the exhaust gas be going faster? Yeah. It's accelerating as it's going out the back, but once it's released, it's not accelerating. Right? It's way lighter, right? Exhaust gas is 3,700 kilograms, right? 10 to the 3 kilograms. The shuttle is 10 to the 6 kilograms. So it's going to be going way faster, way faster. We know it has the same momentum, but it's going to be going way faster. All right. What do we got here? We got M1, that's the mass of the shuttle, 2.04 times 10 to the 6 kilograms. We got M2, that's the mass of the exhaust gas, 3.7 times 10 to the 3 kilograms. We've got the initial velocity of both of them combined is 0 meters per second, because they haven't launched a shuttle in a few years now, but you guys probably remember. You guys are still young enough to remember when they launched shuttles. You watch it on TV. It's not moving before it's launched. The initial velocity is 0 of the shuttle and everything in it. V1F is going to be 5.7 meters per second, and we're looking for V2F, the velocity of the gas. So we're going to say PI equals PF. We're going to say the initial momentum is 0. You could say MVI, but since VI is 0, and I recognize that right now, I'll just put the 0 term in there right away. The initial momentum is 0 equals M1 V1F plus M2 V2F. Mass 1 was 2.04 times 10 to the 6. And this massive space shuttle is only going at 5.7 meters per second initially. Mass 2 is 3.7 times 10 to the 3 kilograms times V2F. What do we end up getting for V2F there? Negative 31,447. Anybody agree with that? Sorry? 427? Agree, guys? Anybody agree with that? Yes? 3,100? That sounds better, actually. Yeah, that sounds better. I mean, we expect a velocity that's a lot bigger, but not that much bigger. Would you get 3,000? Okay, we'll just say negative 3.1 times 10 to the 3. In fact, yeah, as I look at this, I'm pretty sure they're right. Here's why. The mass of the shuttle is 1,000 times bigger than the mass of the, roughly 1,000 times bigger than the mass of the gas, right? So the velocity of the shuttle should be about 1,000 times less. It was in the order of 10 to the 0. This is in the order of 10 to the 3. So I don't know whether it should be 3.1, but 10 to the 3 sounds a lot better than 10 to the 4 or 10 to the 5 or whatever you had there. Make sense? So I think it was, you probably just typed something in wrong in your calculator, an exponent or something like that. Yeah. Now, realistically, there is an issue with this. We don't have to worry about it so much, but you take a course in university in engineering, you go into engineering in university or take more advanced physics, calculus-based physics in university, and you're going to see a question like this, realize that we didn't do this quite right. We made a pretty big assumption here that doesn't change things dramatically for, ballpark, but if you're the actual aeronautical engineer and planning this, you better take it into account. What's the issue? Well, the issue is that the space shuttle releasing this exhaust gas, it's not releasing this exhaust gas all at one time. So it's not like, when you fire a gun and the bullet goes one way and the gun goes the other way as two distinct objects, right? When the gas is released, it gets released gram by gram by gram. So over a period of time, right? Kilogram by kilogram by kilogram. As it gets released little bit by little bit by little bit, it's not all in one chunk like we've assumed here. Okay? Does that make sense? The other thing, of course, is that the more that gets released, the faster the rocket, the faster the space shuttle actually ends up going. So this is an approximation, okay, saying after 1 second, this is what's been released. How fast is it going to be going? Well, it's going to be pretty close to that, but not exactly that, because we haven't looked at it over the period of time. We've looked at it as one event, which isn't quite true for this, okay? All right, and the last question we want to go over is number 10. A 75.6 kilogram volleyball player leaps toward the net to block the ball. At the top of his leap, he has a horizontal velocity of 1.18 meters per second to the right, volleyball to the left, and then we got a volleyball rebounding to the right again. So let's circle some directions here. Remind us that something's going to be negative, something's going to be positive. What's the horizontal velocity of the player immediately after the block? M1, the player, 75.6 kilograms. M2, the ball. What's going to be affected more by this collision between the volleyball and the player? What's going to be affected more, the volleyball or the player? What's going to have a bigger change in velocity? The volleyball, right. Now, which one's going to experience a bigger force? Trick question. Now that I tell you it's a trick question, do you have the answer? Which one experiences the bigger force? It's the same force. Object A applies a force on B, B applies an equal and opposite force on A. Same force. Object, the volleyball is affected a lot more than the player because the same force affects less mass a lot more. All right, so M1 is 75.6, M2 is 0.275. We're going to say the player, V1I, is 1.18. We're going to make that positive. The volleyball, V2I, is negative 12.5 meters per second. V2F is going to be negative 6.85 meters per second. And we're looking for yeah, it is to the right. Thank you. V1F is what we're looking for, right? So we're going to say, again, PI equals PF, M1, V1I. We go, man, I'll tell you, the biggest pain of doing these questions, I think, is writing all this stuff out. Like there's so many subscripts and so many letters, it just gets old after a while. But M1, V1F plus M2, V2F. 75.6 times 0.275 plus, no, that's not right. V1I is 1.18 plus 0.275 times negative 12.5. 75.6 times V1F plus 0.275 times 0.85. So get the number on the left side, get this number, take this number over by subtracting, and then divide it by 75.6, and we should get V1F to be, anybody have that? 1.11 meters per second. So the volleyball player was moving at 1.18 and then ended up moving at 1.11. So the volleyball player slowed down a little bit, right? The volleyball was moving at 12.5 one way and then was moving at 0.85 the other way. Which one was affected more? Clearly the volleyball, right? which is what we predicted because it's lighter. I shouldn't have assigned question B because you don't know what that is yet. Okay, we'll learn that later on this unit, but not quite yet. Elastic or inelastic.